Welcome back. So we were talking about min-max optimization and its connection to generative modeling. We talked about GANs, Wasserstein GANs, and as we saw, they leverage min-max optimization to try to learn two agents, a generator and a discriminator, such that when those two agents reach equilibrium, we can very well learn the underlying distribution and learn the ability to sample from the underlying distribution. But we also talk about the fact that reaching the equilibrium is generally very, very difficult in practice, and we are looking for principal ways to address that. So, and to do that, I want to talk about the fundamental difference between min-max and minimization, because simple algorithms that cannot work in the min-max setting can work very well in the min setting. So there has to be some fundamental difference here that prevents simple algorithms such as the stochastic gradient descent and its extensions to work well in the min-max setting. And the way that I'm gonna sort of, if you will, reveal the differences between min-max and mean is through sort of a simple dynamical system view. And in particular, we're going to talk about the dynamics of a simple algorithm such as gradient descent in the continuous limit. Okay? And this is something we also talked about previously, particularly when we introduced the idea of momentum. Okay? So, if you recall, we said that gradient descent is performing this simple update, and it is kind of associated with an ordinary differential equation that is written here, in the sense that if I use a simple discretization technique, which we call the forward Euler discretization technique, or one-point Euler discretization, we're going to get the gradient descent algorithm. So gradient descent can be thought of as a simple discretization of what we call the gradient flow. Okay. All right. Now next, let's try to also write down the updates for gradient descent ascent that we talk about in terms of solving the min-max problem in this way as well. Okay, so let us define this parameter v, which is a concatenation of the parameter of the generator x and the discriminator y. Okay, let's also define this gradient, if you will, that concatenates the gradient of the objective with respect to x. So this is what the generator uses in the descent step to update its parameter, minus the gradient of the objective or the utility with respect to y. And this is something that the discriminator uses in its update, the ascent step in particular, to update its parameter. Okay. Now, when we form this, then we can compactly write down what is the min-max gradient descent algorithm. Okay. So its update is basically given in this form. It is very similar to gradient descent, saying that I'm going to go from the current solution to the next one by following the direction of f, okay, times some step size or learning rate. Now, in the limits, then, we can again think of this as the Euler discretization of this ordinary differential equation. Okay. So, what's the point here? The point is that these methods look very, very similar. Okay. They are both discretization of certain dynamics, certain ODEs that also look very similar. Then why gradient descent ascent does not work? Okay. So the idea is that there is a very fundamental difference here. Okay. So in particular, the difference goes back to this part. When you compare the gradient of a small f and this capital F, the flow that we define. So these are fundamentally different. Okay. And what's the difference? Well, the gradient of f, as the name suggests, is the gradient of some scalar function. However, capital F is not. There is no scalar function such that capital F is its gradient. Okay. So what's the implication? The implication is that if you consider the Jacobian of the gradient of f, it will be symmetric. So it will be Hessian. Hessian is a symmetric matrix. Symmetric matrices have, let's say, a spectral decomposition with real eigenvalues, and if certain conditions are satisfied, then we see some notion of contraction. Okay. On the other hand, because capital F is not gradient of some scalar function, its Jacobian is not going to be symmetric. So what does that mean? It means that it has some symmetric component, some asymmetric component, or a skew symmetric component, if you will. And the eigenvalues in particular are not real anymore. They are complex valued. And whenever you see complex valued, that I'm sure you've seen in physics courses in particular, you kind of expect some notion of rotation, okay? And this is precisely what is happening here. So why am I talking about Jacobian? Because Jacobian controls the local dynamics, okay? So it describes how a specific flow curves, rotates, and these things will happen when the Jacobian has complex valued eigenvalues. And also it describes how the flow contracts or expands locally. And this happens when basically the eigenvalues are positive. Sorry, they are real value, okay? Such that, for instance, when I have a very nice function that is strongly convex, for instance, and smooth, then I can think of that flow to be contracting. So wherever I start in the space, I'm going to contract and go to the solution, go to the equilibrium. Whereas in the general case where capital F is not, its Jacobian is not symmetric, I may actually rotate, okay, and never reach the equilibrium. All right, so therefore the role of the Jacobian is actually very, very important here, okay? So let's try to write down the Jacobian in this specific way. So the Jacobian of f, you can quite simply write it in two forms as a sum of two components. So the first component is readily seen to be symmetric. The second component is actually a skew symmetric. So skew symmetries are again matrices where the diagonal is zero and the eigenvalues are purely imaginary, and we can associate those with rotational movements. Whereas symmetric matrices have real eigenvalues, and we can associate them with basically contraction and expansion. Okay? So in the minimization case then, when our flow is given by this ODE, the Jacobian of the gradient of f is Hessian, and it is a symmetric matrix. There is no complex eigenvalue. There is no skew symmetric component. And again, we can say that under mild condition, so that basically means that the function is nice, or our step size that we are using is let's say small enough. The system, this dynamical system, is dissipating energy. And you can associate the dissipation of energy with reaching equilibrium easily. Okay? On the other hand, when you have this general flow where capital F is not the gradient of a scalar function anymore, the system might actually conserve energy. And the skew symmetric component, as I mentioned, given that it has these complex eigenvalues, determines rotation. Okay? And the most simple example of this that I'm sure you've seen in physics courses is actually the harmonic oscillator. Okay? So harmonic oscillator is basically described by this second order ordinary differential equation, where you can write it in this equivalent form, in the Hamiltonian form, basically. And if you stack x and y, like we did in the previous slide, so let's define v to be x, y, then we can write that equivalent in this form. Well, this is exactly what we had in the previous case. And in this case, if you calculate the Jacobian, you're going to see that it is actually purely a skew symmetric. So what that means is that we have a system that is oscillating. So when it is a completely isolated system, there is no friction or anything like that, it's going to oscillate forever. So if it has some initial energy, energy is not going to dissipate it. So it is conserved. And that basically leads to the isolation. Okay? So this is exactly the simple harmonic oscillator. Okay? Now, there is actually a very nice connection between the harmonic oscillator that we just talked about and min-max gains. Okay? So it turns out that basically harmonic oscillator is precisely the continuous limit of the gradient descent for this simple min-max optimization problem. Okay? So therefore, in this case, for this min-max optimization problem, I have a flow that only has a skew-symmetric Jacobian. So it means that there is some rotation happening. And I'm not going to basically gain some useful information if I follow the direction of the flow locally. That's why we don't expect gradient descent-based methods to work well for min-max problems, such as this one. Okay. So therefore, as I mentioned, there is this, the fundamental difference between min-max and mean can be attributed to the difference between conservative systems that conserve energy, and dissipative systems that dissipate energy. Okay? So given that we are conserving energy, we have this rotation, like the harmonic oscillator, such that following the flow locally is not going to be necessarily helpful. Okay? And on the other hand, for dissipative system, that's not the case. Flow points to the direction of basically increase, right? And points in particular to the equilibrium. Okay. That's why simple Euler discretizations, for instance, gradient descent that we use in minimization, converge actually very nicely to a stable point when we have a dissipative system. On the other hand, if you have a conservative system, the simple discretization methods such as Euler method are not going to work well. They're just going to push us around and potentially away from the equilibrium, okay, from the stable point. Okay, so generally, therefore, for min-max problems, we need different class of algorithms. Now, in this plot, I'm trying to sort of show how the flow for a dissipative system and the conservative system look and differ. So on the left-hand side, the blue curves, we basically are showing the conservative system, in particular the harmonic oscillator that we talked about in the previous slide. So as you can see here, so these arrows represent the direction of the flow locally. And here I have the equilibrium. So if I start, let's say, somewhere here in this space, okay, so let's say I start here, by following the direction of the flow, I'm just going to basically rotate around the stable point. I'm not going to reach the stable point at all. And in particular, in many cases, we're going to actually, as I mentioned, we're going to move around and away from the equilibrium. Okay. So that's basically due to the skew-symmetric nature of these systems. On the other hand, for a dissipative system, and this is basically a simple optimization problem, I believe f. In this example, I use just a simple quadratic function. In this case, here is my equilibrium, and wherever I start, let's say here, the direction is actually so nice that it always points to the equilibrium. So I can just follow that direction and reach the stable point, reach where I was heading. I want to head. Okay. Okay. So therefore now you have a better understanding of the fundamental difference between the min-max and minimization problems, right? And hopefully you appreciate now the need to have or develop potentially more advanced methods that can deal with the skew-symmetric nature of dynamics that arises in min-max problem. So this is something that we're going to talk about in the next part of the lecture. So we're going to basically see how we can deal with this issue. I'll see you there.